Today we're moving along to our last section of Chapter 10, Unit 7, and today we're going to be talking about finding confidence interval for a difference between two means. And today, since we're going to be looking at this special case, which is the mean difference, which talks about paired data. Please don't confuse it with the difference between two means. That's where students get confused. So we're going to kind of solidify it so we know how to differentiate between the two. So our learning target is just looking at our special case of paired data, and we're going to go ahead and construct and interpret the confidence interval. So a paired data is kind of like a match pair design if you want to think back to the beginning of the course. So paired data results from recording two values of the same quantitative variable for each individual or each pair of similar individuals. So here's an example of a paired from the zinc concentration in 10 wells from an observational study. So they give us our data here, and notice we're talking about well 1 and what the zinc level is at the top and at the bottom. And because we're talking about this one well and we're finding the difference between them, that tells us that we're going to be doing a paired data, a match pair data here. So when the data are paired, the proper analysis uses the difference in each pair. So we're going to go ahead, and they're giving us the dot plot here, and they're telling us the order that we're subtracting. So when they talk about a paired data, and we're doing the conditions for calculating the confidence interval, we need to make sure that the paired data comes from a random sample from the population of interest or from a randomized experiment. We do need to check the 10% condition when sampling without replacement. It is the sample size difference, okay? Less than 10% of the population difference. So now it's going to be the difference. That's going to be the subscript there. The larger or normal sample here, the population distribution of the difference is approximately normal, or the sample size is larger than 30. So the n-diff has to be larger than or equal to 30 if the population distribution of the difference is a known shape and that difference is less than 30. A graph of the sample difference should show no skewness, strong skewness, or outliers, just like before. So when we're doing a confidence interval, we're going to do kind of the same thing. Remember our statistic, plus or minus our critical value times our standard error statistic. But because here our statistic is going to be x bar diff, so we got to find the mean of the difference, plus or minus our t star, because we're talking about mean here, and this is a standard error. So you got to give me the standard deviation of the difference, and then the square root of the sample size of the difference there. And then to find the degrees of freedom, okay, we're going to do the sample size of the difference minus 1. So a paired t-interval for mean difference is what we're going to use, which is our inference method for this section. It is a confidence interval used with paired data to estimate a population mean difference. So caution, the proper method of analysis depends on how the data are produced. So analyzing a paired data, start by computing the difference for each pair, then make a graph of the difference, use the mean difference, so the x bar diff, and the standard deviation of the difference as the summary statistic. So going back to that zinc problem, okay, it says construct and interpret a 95% confidence interval for the mean difference of zinc concentration at the top and bottom of all wells in this region. So we're going to go ahead and do the state. 3 things that we need to put here. 95% confidence interval, and we need to state here that the mu diff is equal to the true mean difference, and we got to put the order bottom minus top, in sync concentration at the top and bottom of all wells in this large region. The plan, well, this is a paired t-interval for mean difference. That's our inference method. And make sure to include the order of the subtraction when you're defining your parameters. That's very important. So we're going to check our condition. The paired data comes from zinc concentration measurements at the top and bottom of a random sample of 10 wells in the region. The 10%, 10 is less than 10% of all wells in the region, and we're going to assume that to be true. Then we're moving on to the large normal sample. So the sample size is small. So notice that the difference in the sample, which is 1 through 10, is less than 30. But the dot plot of the difference doesn't show any skewness or outliers. So notice that I'm plotting the difference. These values are what I'm plotting here. And notice that there doesn't show any strong skewness or outliers. So all three conditions are met. So we're going to move on to the due portion. So our due portion, remember we got to write our statistic. So our X bar diff. Well, how do we get 0.08? Well, we can put these values, just the difference, into our calculator, into our spreadsheet, and use the one variable stat to then find the mean of that difference and the standard deviation of that difference. And our sample size of diff is 10. Very important that you use the correct subscript here. Then we're constructing a 95% confidence interval. So 10 minus 1 is 9. So we can go ahead and use table B to find our T star. And then we're going to go ahead and put our statistic plus or minus our T star times our standard error and do the calculations to find our interval. Now we're going to go ahead and conclude. We're 95% confident that the interval from 0.0430 to 0.1178 milligrams per liter captures the mean difference bottom to top, bottom minus top, in the zinc concentration at the top and bottom of all wells in this large region. So when you're comparing two means in paired data, there are two ways that statistical study involving a single quantitative variable can yield a paired data. Researchers can record two values of the variable for each individual. Okay, so one person, like the one with the well, and two is the researcher can form pairs of similar individuals, which we're going to look at one with twins in a bit, and record the value of the variables once for each individual. Okay, like for identical twins, for example. It is possible to carry out a match pairs experiment using method 2 if the researcher forms pairs of similar subjects and randomly assigns each treatment to exactly one member of every pair. So let's look at the twins problem here. The data from the random sample of identical twins are shown again in the following table. Construct and interpret a 95% confidence interval for the true mean difference in IQ score among twins raised in high-income and low-income households. So we're having a total of 12 pairs, and twin A's IQ, twin B's IQ, and this is the difference. And you do got to give me the order, so they're giving me all that data. So we're going to do the state plan do conclude. So our state, our 95% confidence interval for mu diff, where mu diff is equal to the true mean difference, high income minus low income, in IQ scores for pairs of identicals, twins raised in separate households. Our plan, our inference method here is one sample t interval for mu diff. So we're going to check our conditions. It's a random sample of 12 pairs of identical twins, one raised in a high-income household and the other in a low-income household. And then our 10% condition, 12 is less than 10% of all pairs of identical twins raised in separate households. Now that's kind of sad because the twins should stay together, but in this study, we're going to assume that that's to be true here. Then the normal sample, notice that 12 is not greater than 30. So we're going to go ahead and do our dot plot for the difference from A and B, from twin A and twin B. So we plot this difference, and notice that the number of difference is small, but the dot plot doesn't show any strong skewness or outliers. So all three conditions have been met here. We're going to go ahead and do the do portion. So X bar diff, again, we're going to input that information into our calculator, and we're going to find out what the mean is, how I've shown you before, and the standard deviation. And here, our degrees of freedom, 12 minus 1 is 11. So our T star using the table B is 2.201. Input it in our statistic, plus or minus our T star times our standard error. And we go ahead and get our interval. To conclude, we are 95% confident that the interval from 3.336 to 8.330 captures the true mean difference, high income minus low income, you got to give me the order, in IQ scores among pairs of identical twins raised in separate households. Now, key difference, because this is the big difference that a lot of students get confused. When it is a mean difference, we're talking about a paired dependent observations versus difference of means or independent observations. So think about the mean difference as the twins and the difference of means, which are independent. Remember the northern region and the southern region. The calculations, we're still going to go here. We're going to find the average of the individual difference versus the difference between two groups. Notice the inference method. For the mean difference, which is like the twin problem, is paired t-interval for mean difference versus when it's the northern region and the southern region, we called it a two-sample t-interval for a difference in means. So just make sure that the mean difference deals with paired data and is an average of individual differences, while the difference of means involves comparing the means of two independent groups. And these are last learning targets for this section.